Hello everyone. Today we are looking at another Leetcode problem. This is 3439, reschedule meetings for maximum free time. Now in this problem, we are given a day window which starts at 0 and ends at event time. Okay, so let's call this ET. And other than that, we are given two more arrays. One is the start time, the other one is the end time. So the start time gives us the start of a meeting. Let's say a meeting starts at 5, and starts at 3 and ends at 5. So I will have a meeting like this. Let's say another meeting starts at 7, ends at 11. Then I will have something like this. Apart from this, we are given an integer value k, which is the number of meetings that we can reschedule. Now, given these inputs, we have to find the maximum free time possible by rescheduling K meetings. Okay, so let's take a quick understanding of what this means. So let's say we have been given some meetings. Okay, let's say something like this. Okay, so what's happening is you have 1 1 1 1 1. Overall time free time is equal to 4, but what happens is that right now this time is fragmented. Now assume that I was allowed to reschedule all three of these meetings, so I can push them to the corner so that I can maximize the time. Okay, so I can push them to any corner, but let's say if I make it like this, then all of the free time is clumped together, and now I have the maximum free time was only equal to 1 here. Now the maximum free time is equal to 4, which is actually the size of the window. So now the window has increased to 4. Earlier, each window was of size 1. Even though the overall time is the same, we are only talking about a continuous window here. Now, another thing to understand here is that let's say I have some meetings like this. Again, some random example. Let me also copy this for comparison. All right. And now what I do is, let's say I'm allowed to move two meetings. Okay, so let's say I move this one and move it here, and move this one and take it here. Okay, now let's bring back our other example, which was this one. Okay, now let's assume that now the meetings that I'm going to change are different. Okay, let's say I choose these two this time, so I push them this side. Okay, so what has happened is when I move the consecutive meetings, right, the overall chunk of time that I was able to, the overall free time chunk that I was able to get is greater in this case. What this means is that we have to be moving only continuous chunks. So if k is equal to 2, I have to look at a window of size 2. If k is equal to 3, I have to look at a window of size 3, and so on. So this is a really big clue that we don't have to try all variations. So we're not going to be doing anything like DP here, and we don't need to try out different combinations. So this simplifies the exercise, and so now we're only going to be looking at something that is of linear operation. Now let us look at the constraints that has been given. Okay, so now what they say is the day length, or the time period, the overall time period that has been given to us, which was event time, is actually 10 power 9. This is the maximum upper limit. The lower limit is 1. The upper limit is 10 power 9. Now this range is too large for us to use this in any way. So I cannot travel day by day and look back k elements and then try to figure out something. So this using this part is definitely out of the window. Now let us look at start time and end time array. Now the size, the upper limit of these arrays, the size, the upper limit for the size is 10 power 5. Okay, this is reasonable, which means I can do something with these. All right. So now let us start to put these things together and also understand with one example what this means, right? So let's say I have k equal to 1. Okay. And let's say I am standing here. Okay. So what is the window of time that has gotten fragmented by this particular meeting? Let's see. That particular window of time is this, which is defined by the end of, if this is index, end of index minus 1, and also defined by start of index plus 1. Alright, so as you can see, it got fragmented into T1 and T2. So I can calculate T1. So T1 will be equal to the start of this minus the end of this. So start time of index minus end time of index minus 1. What about T2? T2 will be equal to the start of the next one minus the end of the current one. So this is equal to start time of index plus 1 minus end time of index. Now, if we were only looking at k equal to 1, then I would have just had to slide this window one by one and then keep checking which one gave me like the largest window size, right? So basically in this, if you see, if I take this and move it to this side, then the remaining window length that I have is now T1 plus T2. And so I would have to then check if the max length is anyhow greater than the existing one. So max length, comma, T1 plus T2. This is what I would check. Now, same thing I would do again. In the next operation, what would happen is this window would move to the second element, which is starting here, right? So let's bring back our original meeting. So now the window for that starts like this. Okay, this is what the window would be. So now we are looking at index plus 1. So here we will be looking at the end of index and then start of index plus 2 and compare this with index plus 1. So that is how I will keep shifting my window and keep checking. But the challenge here is that we are not restricted with k equal to 1. K can be any number. In fact, the upper limit that it can take, it goes up to n. So if, let's see what happens if k is greater than 1, right? Let's try to simulate that example. So let's say this is this, let's say this is index. Okay, so now my window of free time looks something like this. This is index minus 1, and this is index minus 2. And this one is index plus 1. So I will define multiple things. This is T1, this is T2, this is T3. So I'll have to compute T1 I'll have to compute T2, I'll have to compute T3, and then I will have to sum them up, because what I will say is that if I move these meetings to this side, then this range is what will be equal to T1 plus T2 plus T3. Now this was for k equal to 2. Imagine if we have k equal to n, then for every meeting, our previous window would be of size n. I mean, taking approximations here. And so my time complexity for this sort of an operation to have a look back window of n and then try to sum up all of the different time components, which are the fragmented time component, I would end up with somewhere something that is of the order of n square. And n has an upper limit of 10 power 5. So n squared is something that is clearly not going to scale. So now we need to start thinking about different approaches, right? So let's do that again. So let's say I am still with k equal to 2. This is my index and this is my index minus 1. Okay, and this is my window that I'm evaluating, where here is another meeting that is ending and here is another meeting that is starting. Now, if you see, what we want to do here is do a sum of this plus this plus this. And in the next window, what will happen is the end of this will become the start of the window. So the window next time will look something like this. Okay, so there can be another one and something like this. So this T2 plus T3 still applies here. Only difference, I have something here additionally and something that I removed here. So one of the things that we can think of is maybe we could use pre-sum. If we have a cumulative array of all of the sums, then let's think about what that pre-sum would be and how we would use it, right? A pre-sum for this will give me all of this, will give me the sum of, so here if for this index it will give me sum of all free time till this index. Same way this one would give me sum of free time till index minus 1. Okay, index minus 1, free time till index plus 1, etc. And so if I look at my original window, which was this much, okay, this gives me the free time that was accumulated till this point. And this one, if I look at the sum that this has collected all the free time until this part. Now if I subtract these two, I get this free time that I wanted to sum up. So now instead of summing up in one shot, I'm able to come to that number. So this is one of the approach. The other approach, which is also quite obvious if we look at the windowing operation, is that, let's say, this is where it was ending, right? So this formed the start of the window. There is one meeting here, there's another meeting here, and then this is where the window is ending. And there is another meeting here. So what happens is I compute the sum of this. Let's say the sum is already computed, and now I have to compute the next window. So when I have to compute the next window, what I have to do is I have to include this and exclude this. Okay, so my window shifts like this. Okay, because I've included that right side and excluded the left side. So this is also something that we can do iteratively, where for every event that we're looking at, we are adding something to the right and removing something from the left. Alright, so I'm going to be showing you the code for both of these approaches. But if you think about the complexity, right, this approach is just going to keep handling a constant or a variable, not a constant, sorry, is going to be just dealing with a variable where you're increasing and decreasing the value and doing all of the adjustments. But here you will have to pre-process and store a pre-sum. Okay, so if you talk about the complexity, this is more efficient. Otherwise, in terms of the execution flow, both of them are straightforward. Okay, so now let's get started with the code. And as we review the code, we will be able to understand the nuances better. So let's first do the pre-sum approach. So we say def max sum, or let's say max free time. All right, so here we got event time, which is an integer, which is the maximum value of that window that we can have. K, which is the number of times I can, or rather number of meetings that I can reschedule. And then I have to erase start time, which is nothing but list of integer. End time, this is also list of integer. Now this has been given to us and we are expected to return the maximum length of free time. So that's going to be an integer. Now let's start with getting our array count. So this is start time. Next, let's pre-process and create pre-sum, which is going to be our step 1. So our step 1 is compute pre-sum array. So pre-sum is equal to start time of 0 minus, there are two possibilities here. One, you have a meeting at the start itself. So start time itself is 0, so 0 minus 0 is 0. There is another possibility where your meeting starts at, let's say, 3. So here you're saying the size of this free time is 3 minus 0. That is what I've added here. So now let's process. For index in range starting from 1. So now I have to start counting starting from 1. This is the 0th free time. So now going from index 1 till n. Actually, we have another case. So let's go till n plus 1. So the last case is about the end time where it ends at event time. You have two possibilities again. You have an event that ends here. You have an event that ends here. So if we stop at n, we will not be adding this to our pre-sum. So it's very important to do n plus 1 or handle it outside. Either way, we have to make sure that we don't miss out the last one which exists after n. Alright. So now my current start is equal to start time of index. If index is equal to n, then we will give event time to subtract from. Alright, and previous n is equal to n time of index minus 1. So when index is equal to n, my value becomes event time, and when that happens, my end time is equal to n minus 1. So this will work. Then we just say pre-sum dot append. What we will have to do is, we are doing cumulation, right? So we should not forget to take the previous value plus previous n minus current start. We do this. Okay, so with this, now our pre-sum array is ready. Now we come to the second part, step 2, where we have to compute max free time. Okay, so we start with max free time is equal to 0. Okay, next what we are going to do is we are going to start from k. Let me explain why. So let's say I have 1, 2, 3. Okay, so this is index k minus 1. This is index k. Now we need to start from index k because let's say everything is looking to its left. That way, because of that, now what is happening is for each of these events, I have coverage on both the sides. You are only focusing on this. But to get the coverage on both the sides, I need to include this one as well. So we will start from this value. Okay, and we are going up to n plus 1 for the same reason, which is this is our event time and this may be our last event. So we do want to compute this minus this to get this window. Okay, that we should not be missing. Now my left value is equal to, so now we are thinking about doing the pre-sum subtraction, which means I took this one. This is all of the accumulation till this point. Now I need to go to this point and subtract this to get this range. Okay, so how do I go that? I'll have to go back, right? So one of the ways that you can do that is to see that if you want a range of k elements, this, let's say, so this is cheat code. So this is the 0th index, right? So you want to go to one element before this. And right now you are at k. So what you need to go to is k minus 1. Alright. So you subtract k minus 1 from k to get to minus 1. So pre-sum of index minus k minus k. So k minus k minus 1 will take you to minus 1. Now if index of minus k minus 1 is greater than or equal to 0, very good. But for the first case, we are going to go out of bound to minus 1. When that happens, we can safely return 0 because we are saying that, okay, we are taking everything in this range and there's nothing for us to subtract here. Now we come to right one, which is pre-sum of index, because we are already starting at the next one, right? That is how we initialized. And so now all we have to do is compare. Let's do that. So max free time is equal to max free time minus right val minus left val. That's it. And then you can return this value. So I hope the pre-sum based sliding window was clear to you. Now we can discuss the one without using any space, which is just the sliding window. Okay, where you have to add one the free time on the right hand side and subtract the free time on the left hand side. So let's go to that one. Let's say we're again starting def max free time. All of the variables are the same. The arguments coming to the functions are the same. So we're not going to add that. Now this is equal to start time. Sounds good. So now if I want to get to a state where I'm sliding the window and when I'm saying that add this one and subtract this one from something. So this something has to be computed for the first time. Then only I can add something to it and subtract something from it, right? So let's do that part first. Okay, let's say current free time is equal to 0, which is going to be used to compute this free time. Alright, and let's say previous n is equal to 0. Now this is going to be helpful because I am doing start minus n, current start minus previous n to get that free time. So for index in range k plus 1. Why k plus 1? Because it will stop at the kth index. What does it mean if it stops at kth index? That means I have k plus 1 elements. What does it mean for me to have k plus 1 elements? Again, remember, if I have 3 meetings, I need to look on both the sets. Okay, so this set, so if everything is looking to its left, this part gets missed. Okay, and to cover this part, I need another meeting to look to its left. That's why I need k plus 1 elements, but all of them looking to just one side. So then what I will say, also I'll add a condition. If index has been reached, okay, which means my k is more than the number of meetings that I have and I happen to reach my last meeting, then for the last meeting, whenever it happened, I need to do this part. So it's a good time because I don't need to check this at n minus 1. I need to check it after this has been completed. So let's do that. Curve free time plus equal to event time minus previous end. And then you can return because there's nothing more to do. So this is the maximum time that you can get by readjusting k meetings, because that's all that is there. There's nothing more for me to compare. But otherwise, I can continue counting. Let's continue with that. Current free time plus equal to start time of the index minus previous end. Now start time of the index is fine. It's not going to be a problem because I am not doing minus 1 here. What we are doing is, because we're starting from 0, there is either 0 minus 0 that is going to happen here, or let's say 3 minus 0 that is going to happen, because previous end is initialized to 0 to start with, so it's going to be okay. And then let's update previous end, which is equal to end time of the current meeting. Okay, that's about it. So this is my first window that we just computed, and this is a valid window. So what we can say is max free time, which is going to keep comparing and find the maximum possible free window time, window length, is something that we will be returning as well. That variable is now going to be set to current free time. Okay, because this is one of the possibilities. This may be the largest window, right? So that is one of the possibilities that we have to consider. Now we start the range, we start the iteration where we add and subtract. Okay, so for index in range k plus 1 to n plus 1. Okay, let's think about k plus 1 and n plus 1 for a bit. Now n plus 1 by now should have been very clear. If this is the last meeting, I don't want to miss this part, so I will subtract event time, and from event time I'll subtract the last n time. Okay, so that's why we need n plus 1. Now let's look at k plus 1. Okay, I'm starting at index k plus 1. What this means is that I have here k plus 1 elements. Why do I need k plus 1 elements? Because remember I said that if there are k meetings, I need plus 1. I need k plus 1 to look to its left for me to complete the free to have the window end to end, right? I cannot just have this window and abruptly have it till here. I need to go till the start of the next one. That is why we have k plus 1. Now k, so in the previous thing we halted at k. We halted at k. Sorry. So this is kth index. Okay. Which means overall k plus 1 elements. Now we have covered kth index. Now we are going to be covering k plus 1th index to the next one. That is what we are going to be adding. Okay. So I hope it makes sense. Right. So next what we do is we need to add something. Okay. So current free time plus what are we going to add? So the new element that we are looking at, we need to add the window created by that. So start time of index minus end time of index minus 1. Okay, but there will be a point where index is already exhausted and has reached n minus 1. Next, when we take it to n, we have to do that operation. So this we can do if index is less than n. Else, we will have free time added as event time minus n time of index minus 1. Okay, this is done. Now we have to subtract something as well. So current free time minus equal to, now let's think this through. Let me just make it a little smaller. Let's look at it with an example. I have 1, 2, 3 meetings. Then I took another one because I wanted this space as well. Now I'm trying to go for another meeting which will look at this, but I need to reduce something. Now let us see what I'm going to reduce. Earlier, my window was this thing, but I had to include this to get this element. Now my window is becoming these 3. And I have to include this because I need to look at this. Now what this means is I am starting at k plus 1. Okay, so this much was already computed, right? I need 3 elements. 1 extra I had to take because I have to also count this one. Now I started my iteration with k plus 1. So this is index of k plus 1. But now I want to remove something. So now I have to remove. So this, which ones have I selected? This is selected, this is selected, this is selected. Okay. So I have to remove this. I have to remove this element, right? So I have to remove this free time. This free time I have to remove. This free time I have to keep because that is to the left of this. Okay. So I hope this makes sense, which means I have to go to the 0th index and I have to look at its start and minus 1's end. Okay. I am already at k plus 1. Okay. So what will I need to subtract from this to get to the 0th index? Very easy. Minus k minus 1. So let's do that. We'll say start time of index minus k minus 1. Okay. Minus n time of index minus k minus 2. Alright. But this can go out of range, right? Because this is 0th index. We are subtracting that with minus 1's n, which does not exist. So let's handle that. If index minus k minus 2 is greater than 0, then only we do this. Else, we just say start time index minus k minus 1 minus 0. Or you can just say start time of that index. That's all. So now here we have subtracted something. Here we have added something. And this is how we have expanded our window. So the only thing left to do is compare. So max free time is equal to max of current max free time minus current free time. That's all. And then you can return. So the time complexity is quite straightforward. It's just order of n. The space complexity for the sliding window, this approach is order of 1. But for the previous one where we used pre-sum, there I had to use order of n. Hope these solutions and explanations made sense. That's about it for this problem. I'll see you again with the next one. Thank you. Bye bye.